If we were to think about what might cause line-of-duty fatalities, I suspect what comes first to our mind is the threat of the fire itself with burn injuries. Last year, 6% of the fatalities were the result of burn. Closely related to that are the products of combustion, asphyxiation, firefighters who run out of air. What many of you would not realize is the internal trauma. Actually, in most years, 25% of the fatalities are due to vehicle accidents and the internal trauma that results from that. And this includes volunteer firefighters who are responding to a call, and it also includes the firefighters who are responding in fire apparatus. The crushing injuries with collapse, other includes rare events like electrocution and drowning. And one of the most horrifying to me, we've now had several firefighters shot and killed at the scene of emergencies. But by far the greatest number of line-of-duty deaths are due to heart attacks. Last year, 46% of the fatalities were due to heart attack. And this is just to give us a little bit of a historical perspective over the last 15 years, showing the number of fatalities due to heart attack in the red line versus the number of fatalities due to burns and asphyxiation. My point in this slide is that the number due to burns and asphyxiation is relatively low. Not as low as we want it, but the number is as low as it is because of education, training, policies, and procedures, and safety equipment. And what I hope to achieve through the research efforts is that we can begin to address this perennially high rate of sudden cardiac events. To put this just another way, many people ask me, do firefighters die of heart attacks more than the general population? They do die on duty more than the general population. The occupational rate of fatality for firefighters is 45% due to sudden cardiac events, whereas the national average is 15%, and the next highest occupational rate is police officers at 22%. So in light of the problems with sudden cardiac event, I think maybe we need to work through this very busy slide, and I did take the class that said a slide isn't supposed to be busy, but trust me, this is as simple as we could get it and have some meaning to it. Let's work backwards. If we're thinking about a heart attack or sudden cardiac event, there's several pathological conditions or processes that can get us there. The most common one is plaque disruption and clot formation. There's also arrhythmias or disruptions in the electrical activity of the heart and circulatory shock due to decrease in blood volume, as you see in hemorrhage. And there's physiological responses that interact with this pathology, and it's really the physiological responses that we'll be studying, and I'll be presenting results on that tonight. And the factors that are happening as a result of firefighting that are driving these physiological responses are severe dehydration, increased body temperature or hypothermia, and the adrenaline rush or activation of the sympathetic nervous system. But just to give you a quick preview, it's clot formation that our research is suggesting is playing a central role in terms of pathological changes. This is a quick overview, if you will, of cardiovascular disease progression and a sudden cardiac event. When we think about a heart attack, in most instances, we're talking about a blood clot that occludes a coronary artery and leads to the death of a tissue. But what we have to realize is that sudden cardiac events are happening in individuals with underlying cardiovascular disease. And by cardiovascular disease, we're referring primarily to the deposition of plaque within the arterial wall. So this is the low-density lipoprotein or cholesterol, the bad cholesterol, that's being deposited in the arterial wall and interfering with vascular health and increasing the likelihood of a sudden cardiac event. Now, we've done some research on this. You'll hear a little bit about this tonight, but most of what I'll be talking about is how firefighting may serve as a trigger for a sudden cardiac event. The question is, how do we go from this chronic condition that actually, I'm sorry to say, begins very early in life in our country due to our dietary and exercise habits. But this, in most of us, is occurring over many, many years, even decades. The question is then what happens to make this chronic condition into a sudden, life-threatening, sudden cardiac event? Well, we're going to have to do just a little bit of physiology. I've been cautioned to keep the physiology to a minimum, so indeed that's what I've done. The interaction of the platelets, coagulatory factors in the blood, and the vessel wall are at the heart of this. When we think about the platelets, if we think about platelets at all, like really, platelets are tiny little cell fragments. When a megakaryocyte breaks up, it breaks up into tens of thousands of these little anucleated cell fragments that circulate in the blood. They typically don't adhere. But something happens when platelets become activated. They grow these little pseudopods, and all of a sudden they become sticky. They change their membrane, they express receptors, and they adhere to the vessel wall and aggregate to each other. And so what we're going to measure in the laboratory are the number of platelets and how much they aggregate. Now, a clot is nothing more than platelets aggregated and enmeshed in a fibrin clot. And this picture here shows the fibrin that forms a framework to hold a clot together. Now, really, that picture has some red blood cells in it too, but essentially a clot is platelets enmeshed in fibrin. And when we're talking about the coagulatory factors, we're talking about factors that lead to fibrin formation. And we'll measure specific clotting factors in the blood. Now, I know you all want more details. I promise to get back to this later in the talk. The vessel wall. We used to think of the blood vessel as a simple conduit for blood, and then we started to talk about it as a semi-permeable membrane that separated what's in the blood from underlying tissue. Now we understand that this blood vessel is an incredibly dynamic structure, the lining of which releases factors that prevent the aggregation of platelets and also controls the smooth muscle in the vessel. Because when you're working hard, and let's use the heart because that's what we're talking about. When the heart is working hard because it's pumping more or pumping harder, it needs to increase the vessel diameter in order to provide more blood flow. And that's all mediated by factors from this endothelium affecting the underlying smooth muscle. In our laboratory, we'll measure vessel thickness as a measure of disease progression, how much atherosclerotic plaque there is. We'll measure stiffness of the artery and flow-mediated dilation. That is the ability of the vessel to dilate and increase blood flow. Let me frame for you quickly how I see the research work that I do. Many people would refer to it as translational research. That is, we investigate the physiological responses to firefighting with the specific goal of improving performance on the fire ground and decreasing the risk of injury and fatality. But the research that we do also allows us to ask some very basic questions that are of interest to scientists and clinicians alike, because firefighting serves as a model for extreme cardiovascular stress. There's no other situation in which humans regularly encounter greater cardiovascular stress because of the heavy encapsulating gear, the heavy muscular work, and the hot and hostile environment in which that work is done. And this allows us to look specifically at the role of heat stress in triggering a sudden cardiac event in a way that you can't do in a laboratory.